have to bring in quantum mechanics to general relativity. When Bekenstein suggested that entropy, he has to how should I say, define, entropy is counted by bits and so on, qubits or whatever. He has to have a unit area, and he bring in this Planck area, Planck length square. But although he recognized that there is an h bar there, by the way, PL squared is proportional to h bar, not Planck length itself, which is proportional square root. Now, so he recognized that he has brought in h bar to the expression, but there's no physics, at least to my knowledge. But here then, Hawking then bring in. We all are familiar with uncertainty principle. Now, so this is actually Hawking he did it himself. After his very rigorous mathematical proof, he wrote another paper saying that if you simply just invoke Heisenberg principle, imagine that around the black hole, outside the event horizon, there were vacuum fluctuations everywhere. Now, if a particle with negative energy falls in, then the other one cannot fall back to each other like here. This, of course, is what we usually have, right? However, black hole with a horizon change the story. You can't just keep on coming back to yourself. Sometimes you have one come in, the other go out. This then brings out, in effect, this black hole loses some part of energy, some delta M, because of this income. And this guy carries the delta M to infinity, and that's the evaporation. And if you keep doing this gradually, this black hole will shrink and die, and disappear. Now, so here's then this Hawking, yes. So this Hawking temperature now links to, again, h bar, g, Newton's constant, the mass of the black hole, c cube and so on. Now, once again, just like the Bekenstein-Hawking entropy, this one again links thermodynamics, quantum mechanics, gravity, everything together. And usually when you see something like that, you say, there must be more story behind this. You don't stop there. Just please dig.
Why the particle can escape the event horizon? I saw nothing can escape.
That's right. Yeah, that's exactly the reason that this guy, is vacuum fluctuations like pairs, right? Yeah. They can find them, they're on pair within delta t, they remerge. But if one of the two in the pair, unfortunately, falls through the horizon.
Oh, they fall through the horizon.
That's right. So they cannot come out. So this guy becomes an orphan, and they just go out. Yeah. So this is due to quantum fluctuation, exactly. Now, so another thing interesting about this Hawking temperature or black hole evaporation is that it is inversely proportional to the black hole mass. Now, so if black hole is evaporating, therefore the mass goes smaller and smaller, then the temperature goes higher and higher towards the end. This is mass, this is temperature. Now, when it goes higher and higher in temperature, when the black hole becomes smaller, you emit more and more various exotic particles. Let's say if your temperature is already higher than 150 GeV, then this black hole can spit out Higgs particles and so on. Imagine that. So that's the black hole. Now, then since it evaporates, it's only natural to ask, what is its lifetime? Now, this is very easy. You go to Stefan Boltzmann law, which says that your energy flux per area of a black body is proportional to the temperature to the fourth power. Right. Now, however, since temperature is inversely proportional to the mass, as Hawking told us, so it goes like 1/m². Now, black hole surface area is proportional to Schwarzschild radius square, therefore m², if you remember that formula. Now, therefore, the evaporation rate is inversely proportional to the mass squared. All right? Now, let's compare. For a stellar mass size black hole, such an evaporation will take 10 to the 67 years, which is way, way longer than the lifetime of our universe up to now. Only to the 10, maybe 100 billion, 13 billion years, 14 billion years, as we know. So that's why I say that although black holes will all do Hawking evaporation, but up until now, since our universe is still only have 13, 14 billion years old, most stellar-sized black holes are relatively young compared to these. They're very young, and this is way away from, and also, yeah, they are very cold because they are huge. Now, the godfather of black hole is the famous John Wheeler. In fact, the term black hole was invented by him. Now, if you happen to have read a popular science book written by Kip Thorne called Black Holes, White Holes, and Warp, Space-Time Warp, whatever, a thick one, which is very interesting. It recounts the history of the development of gravity during the Cold War days, the Soviet bloc under the leadership of Theodorovich. And in the Western camp, there are two sub-camps. In the US, it was led by John Wheeler. The famous names such as Bekenstein, you just heard, Unruh, etc., were all his students during the 60s, 70s. Another camp is in the UK, Cambridge, Sharma. But anyways, so he was asking himself, since things are, you can throw things in, and he said, if I throw my coffee into the black hole, what would happen? Now, another way to ask or to say is, if you throw a computer into a black hole, which is about 7 pounds, let's say 3 kilograms, then this black hole becomes a little bit fatter, then it evaporates continuously. But evaporation is such a thing that it is just heat, just black body. Black body is a very simple thing. It's a spectrum. It's just one parameter, temperature. That's all. There's not that much information. That's what I'm trying to say. Now, but you remember Hawking's formula. It doesn't, in that denominator there's a big M, but it didn't say with a parenthesis say computer. Whatever is the mass, black hole doesn't recognize. There's no hair. Black hole doesn't care whether it was a 3 kilogram computer throwing in or a piece of 3 kilogram rock throwing in. The result is the same. Where's the information gone? So, but see, information is a very interesting thing. Quantum mechanics, we all learned that this wave function psi, if you say, you absolute square it, that tells you the probability of finding the particle at that location x. If you integrate from minus infinity to infinity over dx, it equals to 1, meaning the probability in sum, if you search throughout the universe, you will find that particle. So the information is not lost, which is equal to saying that, with a more kind of physics jargon, unitarity has to be conserved. Physics, recognizes unitarity, quantum mechanics at least. Now, so then people start to think, if there is similarly that black holes eat up our information, but we don't believe that it should be. So would it be possible that the radiation actually carries out secretly the information without our recognition? And so, all right. By the way, this is a book which I highly recommend. It's called The Black Hole War, and that's where my subtitle came from of this talk. So if you are interested. This person is my colleague at Stanford, Lenny Susskind. In fact, after we published our paper, Don Page and I had a long discussion with him for 2 hours through a lot of diagrams on paper like that. Now, in the 1990s, I forgot which year, Susskind and his co-workers Torlasius and Uglum, they published a paper suggesting black hole complementarity principle, which says that the basic requirement of natural laws, any natural law, is that it is consistent with causality. Now, this sounds to be a rather common statement, but applying to the black hole, it's actually implying that. Since black hole, general relativity tells us that there are, how should I say, the locality of a thing depends on which reference frame you are talking about. Now, take for example, if you have an elephant, and that's why I was trying to find a dinosaur, but I didn't succeed. Most dinosaurs I found has a white background, so it didn't look good. I wanted to cover this elephant up. But anyway, if there's an elephant falling in, and okay, this is a fact. Now, if you have two observers, one, A was outside the event horizon, B is inside. Now, for the outside, because of his local clock and everything, he sees this elephant just indefinitely approaches the event horizon, never ending. Just keep slowing down. Keep. Now, the person B on the inside sees that this elephant passes through the horizon unharmed in one piece. And then, well, experts will quickly say, well, this is not true. There's a tidal force. This elephant will be stretched in a very weird shape, which I agree, but it's consistent. Everything is there in one piece. Now, then, it's possible that you have radiation, right? Hawking radiation. So it's possible that this elephant, when finally very close to the horizon, it turns itself into radiation, turns into ashes. Now, this guy, on the other hand, this observer B sees this poor elephant continues to travel to his dome. Now, these two, and the argument is, these two are not inconsistent. Because different observers has a different space-time, they never can communicate because of the event horizon. So there's no right or wrong. They're just not talking to each other. Now, so both are correct, but the interpretations are different. So this is their argument. Now, talking about this whole business, I have to detour a little bit to talk about the entanglement, quantum entanglement. And now, you have heard, everybody has heard the famous cat of Schrödinger, right? I ask you, how many of you knew that this cat was invented, was adopted by Schrödinger through Einstein? How many of you knew that? Okay, none. So this is a opportunity I'd like to share with you about how smart Einstein, just hatefully smart. Now, you know that in 1935, Einstein, and we'll see in a few pages, and his co-worker Podolsky and Rosen suggested this, by now called Einstein-Rosen-Podolsky-Rosen paradox, right? Upon seeing this, and at the time Einstein was already at Princeton, and Schrödinger escaped from Austria to Ireland, in Dublin. They communicate frequently. They knew each other already. And so upon reading Einstein's paper, Schrödinger communicated with Einstein in several communications about this issue. Okay, so Schrödinger came to realize what Einstein was saying in that paper was that the quantum entanglement is not just a property of quantum mechanics, but the character of quantum mechanics. It fundamentally breaks away quantum mechanics from classical physics. Now, I found it very amazing. If you please can go to Wikipedia, you just check Schrödinger and cat, and so it will tell you the story that Einstein, in one of his letters to Schrödinger, said, consider if you have a keg of powder, gunpowder. Then after a while, this keg of gunpowder can be either explosive or non-explosive. Well, I just changed the word gunpowder into cat. That's Schrödinger. So Einstein had already thought all about those things. Now, So, yeah, in German it's called Beschränkung. Now, so entanglement entropy, what's that to do with us? Now, in thermodynamics, just now I said we're talking about the change of entropy. Entropy, how should I say, is associated with the concept of disorder. Now, what's then the quantum informatics or quantum entanglement? And that means that quantum entanglement is corresponding to how intertwined a system is, like this kind of pictorially. If you have something just totally kind of connected, or like this. Imagine you have two systems, and here I already said in I show you in this picture there's an A and B. Imagine the universe is partitioned into two subsystems. Now, because of the quantum nature, non-local nature, you can imagine that the system, the states, inside and outside, are not just talking to themselves. They are actually talking to each other. But they have a very strange habit. They follow this monogamy social order. 一夫一妻制. Okay. So, so they look. It's only one line. This doesn't like the emperor of ancient Chinese. Okay. Now, so these entanglement happens to be the key in answering a few of these questions. Now, and talking about quantum entanglement, usually we mention the von Neumann entropy, right? Now, this was actually a quantum version of another entropy called Shannon entropy. I found that Shannon only passed away not that long ago. Amazingly. Now, this is a bit like what I quoted from Sommerfeld. This is von Neumann, so let's trust it a little bit. He said, when use entropy, this is what he told Shannon. He said, use entropy and you can never lose a battle, a debate. Because no one knows what it is. Okay, now, so here comes Don Page. In the early 1990s, he said, well, I don't believe what. Oh, by the way, I forgot to say, Hawking, after his famous discovery of the evaporation in 74, 75, in 3 years' time, in 78, he published another paper, and exactly the title was, it's the information, this black hole lose information, something like that. So this was his, it started from him, but for a long time he believed that black hole evaporation does result in a loss of information. Now, Don Page, if you have seen the movie Theory of Everything, maybe not, maybe yes, but anyway, Don Page, though a student of Kip Thorne, not though, I shouldn't say though, maybe that's why. He was a postdoc of Hawking and stayed in his home helping him. At the time, Hawking is already, not very good in functioning. All right, and he's a big guy. So now, he investigated and found the following. He said, yes, indeed, black hole keeps, this is the entanglement entropy of black hole. You imagine, black hole has partitioned the world into two halves. One is inside, one is outside. Now, but when it evaporates, you cannot forget about the system B outside of black hole, because now you're collecting more and more early photon radiations, Hawking radiations. So you have to calculate their entanglement entropy. And what he found was that the information actually, at the early time, before the first half of the black hole lifetime, there's indeed not much information leaking out. The Hawking evaporation was indeed pretty much thermodynamical, black light, I'm sorry. So there's not much information until roughly half time. And people now call this half time Page time. Okay. Now, so the lesson I learned is that you need to have a very nice last name. Better not very long like Russians. Then. Okay, now, so halfway down then, the situation has changed. The entanglement entropy goes down. You get mostly evaporating out and mass becomes smaller. So then we call this, before that, we call this black hole being young, after being old. Now, then entanglement entropy, when it's going down, the information carried out by the radiation goes up. And so he said that, so therefore, in fact, unitarity is preserved. Then in 2012, 4 gentlemen, with the acronym AMPS, investigated this issue again and argued that if you want to have unitarity be preserved, there's some problem. Because earlier I mentioned to you Susskind and Colloquia's idea of complementarity. And they found that the conclusion of that complementarity relies on 3 assumptions. One is that the physics should be unitary. 2, local quantum field theory has to be working. And 3, there's no drama when passing through the black hole, according to Einstein's general relativity. Not all 3 of these fundamental assumptions can be consistent. And they found that in order to have it unitary, you better give up no drama. And there is a physical argument for that. I'll show you in the next page. They think that this is the most conservative solution. Now, what does that mean? We recall that in quantum field theory, how many have you taken quantum field theory before? Or taking it right now? Only 1. Oh, I'm sorry. So anyway, let me just say, in the Hamiltonian of a physical system, or Lagrangian, there is this kinetic energy, and in field theory, it's partial phi, partial mu phi squared, or partial mu phi, meaning, well, this is 4-dimensional, so meaning that the derivative of a field and squared, that's its energy. Now, in the case of black hole, I already told you that the geometry, the space-time is not continuous. Remember the structural metric. And therefore, the field value need not be continuous there. Actually, not even less. It's a time derivative, or it's 4-dimensional derivative. So therefore, there can be a pile up of energy there, even just talking about physical terms. So at the boundary, you can imagine, okay, they went instead of a kind of a boundary of nothingness, like in a classical sense. Now they say, well, there's a physical something. It's like it's a very highly concentrated energy, and therefore anything passing through it will be burned into ashes and re-emit. This page is too complicated, so let me skip. So this is pretty much repeating what I was saying. Okay, general relativity say, well, you just pass through. Of course, elongated. By the way, the space-time signatures are exchanging when you're front, inside and outside, as you should know. Now, instead, these firewall firefighters suggest that these things, nothing can go through. There's nothing inside. As long as you come close to the horizon, you're burnt, and then that's how it all emitted out. And that preserves the unitarity. Nothing is kept inside. Everything is ashes. Now, this dates then all the way back to the famous Einstein-Bohr debate on quantum mechanics, or shall we say, determinism versus whatever. And so let's now quickly review some solutions and their pros and cons. Now, was this last year? Yeah. Last year, I wrote a paper with my former PhD student Yan Qing On, who's now at the Nordita Institute for Theoretical Physics, Scandinavian, Northern European consortium. Then this Donghan Yuan from Korea. He's a fellow of LeCosPA. Actually, Donghan, where are you? Yeah, this blue shirt person. Extremely smart. And so we together wrote this big review article in Physics Reports and about information loss paradox and the case for black hole remnants. So let's go through 4 solutions. This is number 1. Number 1 is it says horizon actually doesn't even exist. Isn't it nice? If so, then there's no problem. I'll find this solved. Now, this is actually according to news media. 2014, only 2 years ago. All of a sudden, news media started from London says Hawking said black hole does not exist. Now, actually, Hawking didn't say that. Hawking actually said that the event horizon that we know of may not exist. The only thing is real for black holes is its apparent horizon. What does it really mean? I'll come in a little later. Well, the word apparent is just like English. So it's like a horizon. It retains matter temporarily. But towards the end of the event, it will gradually release it. And towards the end of the black hole life, this apparent horizon and the actual event horizon, mathematical event horizon, combine. Okay, remember. So it was Hawking's suggestion. I even remember I read this news at the time, a couple of years ago. Now, there is a small problem here, because the so-called apparent horizon depends on the choice of your coordinates. And so it is not that so much of an invariant statement. So there's some problem. What's solution 2? Quantum entanglement actually is equivalent to wormholes. And this was suggested again by Susskind and company. Now, so what does it mean? And there was a nice, even rhymed, 好像押韵的 kind of slogan for this idea. ER equals to EPR. That even has a rhythm. Now, what does that mean? ER stands for Einstein-Rosen. Again, in the 1930s, he and his assistant Rosen investigated classical general relativity and showed that there can, even a black hole can have a throat connecting to another something, some heavenly object. That's where the idea of wormhole started from. It's like 毛毛虫可以蚯蚓可以从另外一面钻出来. So this is by now called Einstein-Rosen bridge. Now, then EPR I already mentioned too, having to do with quantum entanglement, non-locality business. And so one side is quantum, one side is classical, GR. And so Susskind said they are equal. These, if you can, through the quantum entanglement, the bridging, Einstein-Rosen bridge, is equal to having this entanglement. Okay, now, so that's an idea. And this is, kind of a beautiful picture about wormhole, all kids like. Now, solution 3. By these two young gentlemen, one is at Harvard, one at Stanford, assistant professors. They say that you actually, there's a small missing point here. When we talk about information, you need to tell us, how did you get this information? According to their analysis, in order to decode, oh, by the way, I forgot to emphasize this following. I wish you would not mistake it. When we say information is preserved, we didn't mean that when the black hole continues to Hawking evaporate, it returns to us the original information of that fallen computer. No, I'm just saying that when you decompose into bits and pieces, that total count will come out. Okay, so yeah, so I think you understand that. So now they say that according to their analysis, if you want to, in order to decode the black hole information, it will take such a tremendous long time that it's will wait even longer than black hole lifetime. And therefore, this is a non-issue. You will never see whether this unitarity is preserved or not, let alone firewall. You don't maybe even need it. Now the fourth one was not as popularly discussed by others, and therefore that's why we volunteered to discuss about it. Well, actually, this is not entirely fair.